Today, I will present an analysis of how digital technologies and mass transfer phenomena are transforming the modern meat industry. Let's start with an alarming fact. Nearly one-third of all food produced globally is waste. That's more than 1.3 billion tons every year. In this context, sustainability and food safety have become essential pillars on the global food system. These are annual global meat production in millions of ton carcass weight equivalent. And I check what is the countries of principal producer of meat. The technologies. The application of smart technologies allow for improved food safety, reduce the human error, optimized automated processing, and the delivery of more personalized and sustainable products. The artificial intelligence uses machine learning and deep learning to generate models that allow us to predict and find patterns in the data. At the same time, the artificial intelligence and deep learning analyze the million data points to predict deviation, optimize the quality control, and anticipate the risk of microbial contamination. A key example is our hyperspectral imaging. This system of capture imaging can box sorting. Also, it's possible to use this same vision to check the quality inspection. Here is possible carcass sorting by sex. Also is possible detection of fecal contamination in carcass. Other interesting technology is the electronic nose. It's possible capable of detecting subtle deviation in spectral patterns or a volatile gas. The use of smart sensors also contributes to reducing the food waste. This device can detect gases such as carbon dioxide, ammonia, or hydrogen sulfide, which indicate the product freshness level. For instance, an increase the carbon dioxide reverses the bacterial growth, while a decrease signals the loss of the modified atmosphere inside in the packing. Convolutional neural networks have been successfully applied to assess the freshness, texture, and color of meat, achieving accuracy of up to 97% in classifying deterioration states. Digital technologies are redefining every stage of meat processing. The Internet of Things (IoT) connects sensors, cameras, and equipment into intelligent networks that collect real-time information on temperature, humidity, and storage conditions. Blockchain technology offers a secure and decentralized solution for complete the traceability of meat products from the farm to the end consumer. In the cold chain, temperature and humidity sensors can record and transmit information in real-time storage and transport conditions to be automatically adjusted to prevent the microbial growth. And blockchain technology uses QR code or RFID target to complete traceability of meat products from the farm to consumer. These databases feed predictive models that anticipate demand, optimize inventory, and detect deviation in the real time. Thanks to connectivity and real-time analytics, this system use early alerts, enabling faster and more sustainable decision-making before spoilage occurs. The experimental results confirm that the integrated smart sensors, microcontrollers, and AI algorithms can serve as a practical and scalable solution for reducing the food waste. The meat is a complex matrix. It's composed of water, protein, fat, and minerals, and interact with the packaging. The word plastic is used to describe material based on synthetic or modified natural polymers, which can molded using heat or pressure. These compounds may include monomers, plasticizers, antioxidants, or even non-intentional added substances known as NIAs. This slide checks what is the plastic manufactured. Here is possible product packaging and environment interaction, permeate, migration, or sorption. The migration is governed by principles of thermodynamics and kinetics, particularly by molecular diffusion and an equilibrium partitioning between phases. This is mechanism influence the migration and the factors. This is the diffusion mechanism. This is the mechanism of the partitioning coefficient and is defined if the ratio of the compound concentration in the food and in the packaging material at equilibrium. Other mechanism is absorption and desorption. Factors that determine the rate and magnitude of migration are storage temperature, time residence, contact area, food composition, concentration of active compound, and packaging material. These are of type of migrant, residual monomers, additives, oligomers, and non-intentional added substance, or NIAs. This is the migration assessment method. Migration of additives from packaging material to food. These are the food simulants. These are analytical techniques, gas chromatography or high-performance liquid chromatography, also Fourier transform infrared. These are the predictive models. For example, this is based in the Fick's law or the Pittinger empirical model that is possible use the same computational models. Globally, several organizations have established specific regulatory frameworks. The European Union regulations has a global and specific migration limits for the plastic material. In the United States, the FDA oversees this aspect under the Title 21 of the Code of Federal Regulation. In Mercosur and Latin America in general, these standards follow the technical principles of the European model. In Asia or another regions, follow regulatory frameworks partially aligned with United States and European Union. The migration of chemical compounds from packaging into food is a food safety issue due to its potential impact on consumer health and the sensory and nutritional quality food. This is the literature. Thanks.